We are going to be having at least 8 different classes for this particular course, and outlined on the slide are some of the topics that we're going to cover, or the main topics. We might have deviations here and there, but these will be the main topics that we're supposed to cover. Week 1 will go to foundation analytical thinking, Jupyter workflow, and first analysis. And the hope is that there was supposed to be a week 0, which is supposed to be the period when you do all of the installation of Anaconda, get your Jupyter lab working, and a couple other things that you need to do to prep your environment for the work we are going to be doing. So, which would be a very good segue into week 1. So by week 2, we'll be focusing on data acquisition, APIs, collecting web data, and data wrangling. Week 3 would feature cleaning that data, exploratory data analysis, and we will now apply some of what we learned from those to the popular Titanic project, which is a project that is really very popular with the data science community. Essentially, what's happened with the Titanic. And then week 4, we go into regression modeling and evaluation. 5 will be classification, matrices, and clustering. We go into time series, forecasting, and scalable analytics. And by week 7, we would have applied AI, a bit of machine learning, deep learning, and then we talk about responsible AI ethics, and all of that. The world of data science has changed tremendously, especially with the advent of AI. We're going to be focusing on a bit of that in week 7. As you can see, this is a lot of work for the various weeks in this course, but we would do what we can to get through some of this content. So in your, what you would call in Google Classroom, you should have a couple of additional recommendations for materials that you need to study in addition to what we're doing here already. And then, of course, finally, we're going to have the capstone, which would be a combination of all of what we've done in this particular class. So data, as it were, data is really very important, but data, some will tell you that data is the new oil and all of that. But the truth is that data is not useful until you've been able to go through some really very important processes to finally get to some kind of intelligence that helps you with decision making. And what we highlight on the slide here is actually that particular process that starts from the very foundations, and we're going to talk some more about that later. The acquisition of the data, cleaning of the data, and the exploratory data analysis. We go to regression, classification, forecasting, and sometimes, we will end up in AI ML. So this essentially will be how we try to talk about data in this class, and that would essentially be our roadmap for the class. And through each of these clusters, right, we'll be able to just understand how data works and how to go from gathering your data, cleaning up your data, analyzing that data, curating the data, and then making sense of that data. So essentially, it's a progressive build. In other words, you can't jump from chapter to chapter or from topic to topic. You have to follow this particular process to be able to, really understand what's going on. So for today, we are going to have a couple of things to cover, but I'm going to, start with the foundations of data science, essentially. So for this week, the goal is to build the vocabulary, workflow, and the mindset of the entire course. So just to help us understand how uh, the course is going to be structured in terms of how you want to begin to look at this course, you know. for starters, a lot of people, when it comes to data science, they just jump straight into data science, begin to use all of the tools and all of that. We're going to take a slightly different approach. And that approach involves understanding what the problem is, first of all, before we even begin to decide on what the tools are. Setting out our objectives. What is it that we want to achieve? What is the problem, right? And then we hypothesize about the possible solution. And then we can now go into identifying key tools that can be used to solve that problem based on the hypothesis that has been developed. So the goal, therefore, is not to memorize tools. It is to learn how data scientists, right, structure uncertainty. By the end, as a student, you should be able to explain the life cycle, the life cycle of data, the roles in this discipline, and then you develop a couple of analytical thinking pillars, and then the purpose of the notebooks, which will be something else that we go into, because I've prepared a couple of notebooks that can help you now actually do hands-on work, working with data in Jupyter Lab or Jupyter Notebook. And then it would the notebook would encompass all kinds of data related problems, that would involve interpretation, visualization, and eventually I would expect you to do some reflection, which is where learning actually happens, about the entire exercise that you go through in some of those practical notebooks. So after week one, the goal of this class is that we should be able to, as a class, define what data science is in relation to analytics, statistic computing, and actually the, domain expertise. And what does that mean, right? So being a good data scientist or being a good analyst, there's an element of you understanding the domain that you're working in. So domain expertise is very important. Computing, has a role to play in computer science, and of course, statistics and analytics. All of these are aspects, that have something to do with data science. So in defining data science, these are some areas that kind of intersect in what would look like a Venn diagram in articulating what data science is. The second thing you should be able to walk away with is to explain the difference between data, information, insight, recommendation, and action. They are all different things. You want to identify the major roles in data science team and how they collaborate. So when you get into a typical data science team, there are all kinds of people working together. So one of the things we will do today is to also help the class understand those major roles within data science. It's not just the data scientist that is there. There are other professionals that sit within a typical data science team. We should be able to describe the data science life cycle and the quality gates at each of those stages in that cycle. And then we need to be able to also frame a vague business issue into a testable analytical question, right? So we have to get a particular problem and then analyze that problem. That's essentially what we're talking about there. And then we need to be able to use Jupyter Notebook as a professional analytical narrative for the class. So this will be some of the key concepts, and we start with the definition of data science. So it's a discipline process of using, so the word discipline is really very important, because you want to have a structured way of doing things. You don't just play around, and that's part of what we're also going to be learning in this course. What's that disciplined way of processing data? So data science by itself, is defined here as the disciplined process of using data. Data is very important. Computation, statistics, domain expertise. Like I mentioned, domain expertise is the industry you're working in. So the way you do data in banking is going to be different the way you do, even though the principles are the same, but it's still going to be different than the way you deal with data in healthcare or in aerospace, right? You need to understand that domain, or at least you need to have someone with domain expertise to be able to work within that team to help you understand what's going on there. And in it, that understanding is very crucial to building out a data pipeline and understanding what the situation on ground is before you begin to build. So we want to be able to, you know, get all of these processes together of using data, computation, statistics, domain expertise, and communication. Communication is really very important. When you solve a data science problem, you need to be able to communicate that problem. Sometimes we hear of all kinds of news articles, right, where uh, you know, a typical journalist is just trying to tell the story about something in a research paper and they completely bungle it, right? As data scientists, usually I think you would have a lot of analysts do that. This is the domain of you being able to communicate the findings from your data analysis to your stakeholders. And a typical enterprise organization, right? One of those key stakeholders that needs to understand what the data is saying is leadership, especially people in the C-suite, managers, and all of that. Once we gather all of this information and we analyze them, we need to be able to communicate it to them in a snapshot. And that's where, for an example, dashboards become very important. So you have things like Power BI, being one of those really valuable tools to communicate your data science research findings or data science analysis findings, right? You need to be able to communicate it in a way that is very digestible, with to enable leadership make quick decisions with some of that data. So, and the goal is to produce reliable, insightful prediction, explanation, or decision support. So they need to be able to make decisions or even predict, quote unquote, the future, right? With all of that data. So essentially, it's not one tool, it's not one algorithm, or nor is it one program language. There are tools, absolutely. There are awesome algorithms. There are in multiple programming languages. For example, Python and R are really very good languages. But then it's not just one of those. Instead, it's an end-to-end way of converting uncertainty into evidence-based action. In other words, I have this input, which is my data. It goes through a process, and then what it gives me is a clear way of being able to tell what is happening now, what has happened in the past, or what will happen in the future. So, the value chain of decision, because in a previous slide, we're talking about, hey, what's the difference between that? There is a difference between data, information, insight, recommendation, and an action. So for each of these layers, right? For data, for example, the layer of data, what we are asking, what facts do we have? An example is your individual sales transactions. So maybe you have them in an Excel sheet, all of that. So data is about the facts that you have right now. Information is when you now organize that data, right? So that it begins to tell a particular story. So for example, you can go from your individual sales transactions, which maybe you have on an Excel sheet, and all of a sudden you organize everything by months and by regions and all of that. And all of a sudden, that information that you get there, what you get there is your information. The point is, while data is about what the facts are, information is about how you organize those facts. So like the monthly revenue by region, all of that came about from a bunch of linear, like, sequential, what would you call it? Data in structured data in, maybe an Excel sheet or something. But after you've organized it in a certain way, that's how you get information. And then from that information, you can begin to actually look at things, and all of a sudden you might see some trend, right, emerging. So for example, the southern region, right, we created this dashboard, right, that has the monthly revenue by region. But then you begin to look at the pattern between all of the regions, and then you see that the southern region declined sharply. That will be a pattern. You're beginning to see it. And then recommendation is about what should be considered. You want to investigate the customer retention and promotions. So from that data, we can actually tell a story, know what's going on, and make recommendations to leadership. And then action is about what can be done about it. We can now, for example, in this particular case, target retention calls and pricing reviews. In other words, we identified that the problem was there were issues with customer retention and promotions. And then to try to mitigate that issue, we have targeted calls to these customers and do some kind of price review, maybe things are too expensive or whatever. But that's the action you take, right? So a common misconception is that data is everything, right? It's automatically the truth, and data is not automatically the truth. And that's why you see people can manipulate data, they can adjust data, they can present data in different ways that help tell the story they want it to tell. So data is really agnostic. It is agnostic, right? It's neither good nor bad. It's just there. You just have to use it for what it's meant for and not misuse data. So, and sometimes you might actually be using data correctly, but then you're painting an incomplete picture, maybe because the data that is required to reach the conclusion that you are attempting to reach, is not available. You just have incomplete data. So data can be incomplete. It can be biased. That also is true. It can be stale. In other words, the world has moved on. Things have changed. The data doesn't really represent what's happening now. It can also be mislabeled. It can be duplicated or collected for a purpose different from your project. So if when it was collected and the variables that were collected don't match the project you're doing now, that's data is going to tell you very very give you very wrong results. So data reflects measurement choices. It does not perfectly represent reality. So if I have data and I'm supposed to collect data, it is the variables. In any particular situation, you might have the option of collecting 10,000 different variables, right? If you decide to choose certain variables that are not necessarily representative of your project, there's nothing wrong with that data. The problem is just that you did not make correct measurement choices, and therefore it does not perfectly represent the reality that you're trying to evaluate. So a model can be mathematically correct and still answer the wrong question. That's very important. Very, very important. And a lot of times that happens because of the data that was used to build that model. Even though algorithmically it's actually correct, but it could, you know, still answer a wrong question. So professional analysts, they tend to treat data as evidence to be interrogated, not as an authority to be obeyed. The whole point of this slide is just because we have data and then we have some kind of outcome, you should always be skeptical about data, because data could just essentially be garbage in, garbage out, right? Because what you put in is what you get out. So these are different aspects of what you will call the field of data science, because I wouldn't call it data science. That's why the class is a bit of data science and analytics, and I'm not even sure that fully captures what the data discipline is about. But for some of the terms that you're going to keep hearing in data science will be something like analytics, data science, machine learning, artificial intelligence, deep learning. All of these things are very related, but again, at the same time, they are very different. Analytics essentially describes and explains patterns. So, and that's where you say someone is a data analyst, most of what they are doing is working with dashboards, reports, key performance indicators, diagnostic insights. And typically, an analyst, right, or the field of analytics involves using data from the past, right, to make meaning of data from the past. In other words, we get all of that data, we organize it to be able to sequester information, and then that information, we will present that information on dashboards, reports, KPIs, and you know, um, serve them as some kind of diagnostic impact. That's what analytics is about. But data science is the end-to-end data-driven problem solving. Data science can include, it does include a lot of machine learning, artificial intelligence, deep learning. It involves, that's why it says it's end-to-end data-driven problem solving, where you're, using data to create models, you're running digital experiments, your forecasting and decision support. While the analyst, right, focuses on understanding the past, the data scientist is more interested in predicting the future, right? So they are focused on predictive analytics and prescriptive analytics, right? Those are the kind of things. In other words, we have all of this data from the past. How can we use it to extrapolate into the future? And how far into the future can we reasonably and accurately project into the future? And then what happens if my data, the model I developed, right? The data that was used to develop it has gone stale. Maybe I need to get more fresh data and refresh those models. That's the domain of the data scientist. And then we have machine learning, which focuses more on algorithms that learn patterns from data. And like I mentioned, that could be a part of data science. Artificial intelligence, these are, in fact, machine learning, artificial intelligence, deep learning, they are essentially subsets of each other. So, for example, deep learning, machine learning is a subset of artificial intelligence, and intelligence, deep deep learning is a subset of artificial intelligence, while machine learning rather, and I'm referring to machine learning here, is a subset of artificial intelligence, while deep learning is a special case of machine learning, right? So they are all kind of connected. But again, at the end of the day, what are we trying to do? We're essentially, all of this is about intelligence. And when it comes to the field of data, it is trying to, essentially what we're doing is trying to use all of that data to build out models that can help us predict the future or prescribe solutions for the future. And of course, we're going to touch a little bit around AI, because AI is really, really important today in the field of data. So what are some of the roles? I already mentioned, uh, and all of these people could actually be working together in a data team, right? So you have the data analyst, the data scientist, the data engineer, the machine learning engineer, and then the domain expert. I mentioned the fact that the domain expert is really very important because they understand the industry all of these people are working in, and then they can actually explain to you how things work within that industry, what is important, what's not important, how are things lined up within that industry. That's what a domain expert does. So the machine learning guy is the guy that helps with all of those AI, deep learning, machine learning, essentially helps with production of machine learning systems, uh, model set, serving, and then monitoring. So, and what is the typical question is trying to solve? Can this model perform in real use? The data scientist essentially builds the pipeline, right? So that everything flows through it, essentially. Can the right data arrive reliably and securely? We want to build out that infrastructure. That's what the data scientist does. Data engineer, sorry. While the data scientist, their job is to develop models, do inferencing, experimentation, and interpretation. Essentially, what predicts the outcome, what explains the variations, and all of that. So that's what is data scientist does. So everybody here works together to build up the system, to create the models, and then put the models in production, and then the domain experts supposed to help, contextualize the models that will be built for that specific industry for which it is being built. So most serious data science products are too complex for one person to own every layer perfectly, and that's why we have all of these people working together. A model is only useful if data pipelines, domain logic, interpretation, and deployment all work together. Role clarity, reduces rework. In other words, if you're in a data management team, everybody needs to know what their task is. It doesn't mean that you can't cross lines sometimes, but it has to be clear what everybody's supposed to be doing, because that can be helpful. That can also help make sure that the ball is not dropped. Analysts do not guess what engineers can provide. Engineers do not build pipelines without business context. In other words, they need a domain expert, right, to work with. So everybody knows exactly what they are doing. So in this course, we'll practice the core workflow, even if they later specialize into one role. That's what we'll be doing here. And as a participant in this course, you're going to learn what everybody does, even if at the end of the day, you end up going to do something else. So now we go into the data lifetime cycle, the data science life cycle. So you start typically with a problem. After and this is where the domain experts, the journey of the domain expert is really very important, right? So everybody sits down and we determine what the problem is, right? And then how can we solve the problem? After the problem has been determined, right? That's when you go to look for the data, collect all of the data you need to solve the problem. And then the next thing you do is you clean, you do some kind of exploratory data analysis, which is when you pull some of the data and explore that data to see how, for example, if it was an Excel sheet, we want to see how many columns there are, right? How many rows there are, what are the various column headers, then are there any missing um you know any missing data within the Excel sheet. All of those things are the things you do, and maybe you plot out some graphs and fast graphs, histograms, and all of that to be able to really understand the data. So all you're doing is you're digging through that data, and using all the data science tools available to get a sense of what's in that data. And then after the exploratory data analysis, then you go into cleaning the data. And what does cleaning the data mean? It includes everything from, do you have duplications that are not supposed to be there? Do you have, say, in a place where you're supposed to have numbers, do you have letters? Can we remove that? Maybe somebody entered something incorrectly and all of that. You want to be able to clean up all of that. And in some cases, depending on what kind of data is, you might want to merge some columns, or you might want to create um, derivative variables, compound variables, all kinds of things. That's what you do in cleaning an EDA. And then you want to it's from that you now begin to build your model. You analyze and you build your model. Sometimes that's where you also inject machine learning, AI, and all of that at this point. And then after that, you evaluate the results that the models are giving you, and then we communicate that problem, right? We need to be able to communicate the results to stakeholders so they can know what's going on. So you will notice that this is an iterative process. In other words, it doesn't have to stop, right? You can keep making things better and better. That's why it says this, the life cycle is iterative. Communication often reveals that the problem needs reframing or the data needs improvement. So that's how you keep going. You know, if any variance is noted, you go back to the problem box, and then you keep going on and on until you get something that really makes sense for you. So these are some life cycle quality gates, right? Places for each cycle that you go through. Take some of the things you need to check, before you go to the next stage. So one of those is your problem definition. The question is specific, it's answerable, and decision linked. What does that mean? A lot of times somebody gives you a project, a data project, right? I know, and I've had a couple of those. Somebody has an idea of what they want to do, but the problem is not specific. To really solve a data science problem well, that problem has to be specific. It has to be something that is also answerable, right? And it has to be linked to some kind of decision. It needs to be solving a problem. So sometimes we can, and a failure mode, right? If you skip these quality gates, what happens is you might end up doing beautiful analysis. Earlier I mentioned and I called it garbage in, garbage out. You might be doing a very beautiful analysis, but then you're solving the wrong problem. Just because you're driving doesn't mean that you're getting to your destination. You might actually be heading away from your solution. So when it comes to data collection, data is relevant, it's accessible, and ethically usable. That's one thing you want to check when you're working on a project. You have to make sure that the data is available, because in data science, as you can see, everything is about data, right? Data is so important that the discipline would not exist if there is no data. So, therefore, for a project to be successful, you want to make sure that you have relevant data. Relevant data is also very important. If you go collect data that would not answer the question that you want it to answer, it might actually, your model might work and everything, but it will be answering a question that is completely different than what you're asking. It has to be accessible and particularly ethically usable. There are certain data that you cannot use because it's just wrong to use those data, right? Or it is illegal to access and use that data. So those are some of the issues. So when you go through these quality gates, that's one of the things that's really very important. So if you don't do that, you might end up with a situation where you have missing or non-compliant evidence. And then the preparation, when you're doing the data preparation, data is clean enough for the intended method. So you have to make sure that you clean the data. And we're going to when we go into our Excel sheet and all of that, where we will have to go into a place where, we have to clean data. And if you don't clean up your data, it might severely and seriously affect your results. And that's why a failure mode here is garbage in and then garbage out. So when we come to the modeling, we want to make sure that the model matches the data type, the method matches the data type and the question. And, we should be able to go into different kinds of data, structured and unstructured data and all of that. We need to be able to make sure all of that for us to be able to build a good model. And then evaluation. Once you have built your model, you started testing it, you started doing inference. One of the things that you would notice is you're going to be gathering a couple of matrices. One of the things you want to do is to make sure your accuracy measures, recall, precision, all of those things, right? you want to make sure that it aligns with the consequences, right? And if you don't do that, right, all of a sudden you have false confidence. And then when it comes to accuracy, when it comes to recall, when it comes to precision, what might be good for one project is not necessarily good for the other. In some industries and some projects, some of the things, problems you're trying to solve are time critical, and the precision is really very important. In those cases, your matrices, will be different than, say, if you're working for an industry, or working on a project for an industry where, for example, precision is not, you know, really that important. Communications. One of the things you want to make sure is that your findings are understandable and actionable. I did mention stakeholders in the C-suite, business colleagues, and all of that. Sometimes they need all of this data to solve problems, and this is where it becomes very important that your findings are understandable, they are presented accurately, and then they are also actionable. Or otherwise, what will happen is you do all of these models, do all of these beautiful things, and guess what? Your work has no organizational impact. And when your work doesn't have any organizational impact, guess what? Your employer begins to think about, do we really need the data science function here, because it's not contributing. But imagine where you go in there, collect existing data, identify a real problem in the company, and help the company save $1 million, right? Now you are talking. So, and these, um, you know, a lot of the things I did mention right now. So I would be keeping this. I will be leaving this part of it for the class to, or individuals to just study, but I'm just going to scroll slowly through them. Problem definition, you know, the framing of the bad framing, good framing, all of that is really very important, how you frame a problem, but you need to be able to define your problem very well. So an example of weak framing is, why are sales down? That's not a good framing. A better way to ask that question is, which customer segments declined over the last 3 months? You can see, if we go back to what we were talking about, you know, the question is specific, it's answerable, and it's decision linked, right? So we're asking for specific problems. So for example, improve student performance, that does not make sense, right? You want to ask something like, what attendance, assignment, and study variables associated with final year performance? So you can see that the framing of this question is strong, it's specific, you know, it's answerable, and it's decision linked. So you keep going, and then you see different improvements. Understanding customers. Can we predict which customer group shows similar behavior and require different retention strategies, right? These are all different ways you can frame this. Data collection, different ways of collecting data, kind of APIs. I think there's a bit of that in this course, spreadsheets, logs, and all of that. Data collection should be guided by relevance, sufficiency, legality, ethics. Relevance, very, very important. Legality, ethics. For supervised learning, labels must be defined carefully, and we should talk about this, about AI, supervised learning in AI. Every data set needs a source node, where it came from, how it was collected, and what it may omit. And then this is where we go into the EDA. The data collection is often the most time-sensitive part of the project, right? Data preparation, because real data sets are messy. So you want to go in there, clean them, and, you know, substitute whatever needs to be substituted in terms of, are we going to do some addition, subtraction, divisions, which is where feature engineering, when we now begin to choose our variables, feature engineering now becomes important. And then EDA, which I did mention, explorative data analysis, modeling. Now, a lot of our models already exist, right? But when we now get our data, we want to find a model that is representative of the patterns in our data, right? We'll do some regression. Just because a model is complex, doesn't mean that it is better. So one of the things you want to do when you choose a a model and you're testing it out, it's a model that is a best fit for, for the problem you're trying to solve. So evaluation, yeah, there are all kinds of tools that are used for evaluation, and we're also going to see some of that in practice, how to use some of these tools, and we have regression, some matrices that are used within regression, to measure. A lot of them are measures of accuracy, for regression, for classification, for clustering, for forecasting, and then for recommendation and ranking. So, and these are all data evaluation tools. And then this is about communication. It translates technical work into decisions, not just charts, right? I think we talked a little bit about this. So I'm gonna, so I don't flog this deployment and monitoring. Eventually, your models are going to be deployed, but they also need to be monitored. And that's where the data scientist and the data engineer play a role, because sometimes everything is working fine, but guess what? The business, if it's business data where you're doing some business analysis, the business environment begins to change, right? In other words, the underlying data that was used to create that model begins to change. Guess what? The model is no longer performing as well as it should. And that's where the data scientists and others would have to go out there, get more data, and then refresh that model. So there are issues around deployments, how to go about deploying them, and then eventually monitoring them. So it's a never-ending loop that just keeps going round and round. So I think I'm going to stop here for this slide and then continue later. And that will be the analytic thinking, the four pillars, and then framing problems, and then going to the Jupyter notebook. Okay. Questions?